نحن في سكيلز بيت الخبرة، ملتزمون بالجيمات الثلاث: جديد، جيد، جدوى.
This is viscoelastic material. And again, what have we done? We've done the classical methods. Maxwell. Kelvin and Voigt. And Zener-Von. And then we start looking at modern models. We did so far the GHM, and then the fractional derivative, and then today we'll do the last one, which is the augmented. Before we describe this, I just want to say one more thing. Is we did also identification of viscoelastic material model parameters. And we've done this for the GHM and the fractional derivative. We used here MATLAB optimization. Toolbox. In the case of GHM model, we put the constraints on. All the parameters have to be positive. constraints to ensure that we get the minimum and the maximum modulus. To obtain the G minimum and G maximum. In the fractional derivative, we did not impose any constraints because all the parameters are non-physical parameters. Here we use the subroutine constraint, and here we use the subroutine minimum S. Okay, one important thing again here. In the GHM, we augment the dynamics of the physical system by an additional degrees of freedom to account for the viscoelastic material. So the system dynamics with the degrees of freedom of the original system are augmented with additional degrees of freedom of the viscoelastic material. Same thing that we've done here, we're going to do here. And that's where the augmented, the last thing that we've done, which is number 4, is to develop the master curves or the superposition curves. Temperature, frequency, superposition graphs or plots. Okay, today we'll begin the augmented temperature field, but before we do it, I just want to do a little on the side here. Piezoelectric materials. This might be look off, but it's not off. It's in the main stream of what we're trying to do. And for the following chapter, we'll take this piezoelectric material and we put them in a network that we can tune it to the structure dynamic. We can use this as a damping material. Okay, piezoelectric material are materials that have two effects. If we squeeze this material, we generate electric output. So this is the material, and we have here mechanical, load, and then we generate electric output. And if if we have it in this form, then this is called the direct piezoelectric effect. And the material can be used as a sensor. So for example, we apply pressure, we generate electric voltage proportional to the pressure. So many applications, this can be used as a sensor. In the structure vibration, you bond this material to a vibrating structure. When you stretch the material with the vibration, you generate electric voltage proportional to the vibration. Okay. And then the second part here, if we take this material, and then we have here electrode. Of course, here also we have electrode and electrode. And this is the piezo material. And if we take this material and then now apply voltage on it. Then this material will expand in all directions. Expand like this. And it will expand in this direction, and it will expand in the perpendicular direction. Okay. We apply the voltage in this direction. This direction is called the direction 3. If we expand and measure the expansion in this direction is called 1. So for example, this is 4 applied voltage. In direction 3. And the material in this form operates under the converse piezoelectric effect or the indirect piezoelectric effect. And if we apply voltage, we generate mechanical motion, so it acts like an actuator. So here, this is the converse piezoelectric effect. And the material acts as an actuator. I'm going to only work in one-dimensional motion in this class. Okay. Now we can write down the constitutive equations of piezoelectric material. These equations relate, for example, the strain to the stress to the electric characteristic, which are, we'll call them here, electric field. So I can say the strain, unfortunately the strain looks like this, S. And the stress also unfortunately is called T. And the electric field is called E. So now I can relate the strain to the stress. If I don't have any electric voltage, so this is conventional material that we're used to. We can say here is 1 over Young's modulus and we'll just say here E modulus for now. We'll give it a better name in 1 minute. Okay? And then, if we don't have stress acting on the material, if we don't have any stress acting on the material, and we apply electric voltage, then this material will expand. Okay? If this is zero, I can generate strain in the material motion by electric voltage, and there is constant of proportionality. This constant of proportionality, in this case, I'm applying voltage in direction 3 and generating strain in direction 1. So this is called the D3-1. Now if I have the two effects, I can generate strain by stretching the material mechanically. Apply mechanical forces on it. And I can also stretch the material by applying electric voltage. So if I have the two combined, then I can apply the superposition for linear system and I have plus. Okay? And I'm going to take 1 over Young modulus and write it down as S small s. If I apply mechanical stress in this direction, I will generate mechanical strain in the same direction, and the relationship between them is this small s, which is, we'll call it S1, 1, because I apply stress in one direction and the generated strain in the same direction. And this number is nothing but the reciprocal of Young's modulus. So we'll call this number the compliance of the material. Okay, so mechanically we have all what we need. This is mechanical. Characteristic of the material. I can also look at the electric characteristic. So I can say, for example, the current that I generate is related to the electric field. In piezoelectricity, we will not deal with current for now. We will deal with charge. And we will not deal with charge, we will deal with charge per unit area. So now we can write down here something called the D. Let me write down here first. This is strain, this is stress, this is electric field, and the electric field is defined as voltage per unit thickness. So for example, here in this case, I'm applying a voltage V on the material. The material thickness is T. Then the electric field is V over T. V over T. We want to write down the electric characteristic of this material. So I can say the current is related to the voltage by the resistance of the material. If I put it in units of charge, this unit is called, this D is called electric displacement. And it is charge per unit area. So this is equal to, if I don't have any stresses, then I can relate the charge to the electric field by the permittivity, electric permittivity. Now if I just leave it as it is, then we have the charge here. The electric displacement, which is the charge per unit area. Electric charge. And then the surface area of the piezoelectric material, which is this surface area. Equal to, if I don't have any stress, then this will equal to epsilon, and I'm writing it now as epsilon, and then E, which is V over T. Now let's clean this equation and write it like this. The charge, we know it is the integral of current dt. And this will equal to epsilon v over t. Now I'm going to rewrite this equation as voltage is equal to integral of current, and this will be epsilon A over T. And we know for any capacitive element, I can write the voltage and the current, and this term will be the reciprocal of the capacitance. So this will be 1 over C. So this says now that C will equal to epsilon A over T. So if you have a capacitance and you want to get large capacitance, you make the area very large, or you make the two electrodes very close to each other. So you can increase the capacitance. So for the piezoelectric material, that's what we have now. If we don't have any effect here. Okay? So now what this equation is saying, if I apply voltage, I can generate charge, or I can generate current on these two surfaces. This is very obvious. The material acts like a capacitive element. If I apply voltage, I generate charge. Okay, so this is, in effect, Ohm's law. A relationship between voltage and current. Voltage and current. But this material also, if I apply mechanical stresses on it, I generate current. So the current that we generate comes from two effects. First, when the material acts as a passive capacitance, or when I apply voltage, apply mechanical loading on it, I generate electricity. So now I can put here also another effect, T, and then here we'll see that this is also 3-1. So now we can look at these two equations like this. I can think of the first equation as piezoelectric material used as an actuator. So when I apply voltage, I generate strain, mechanical strain. Here, when I apply mechanical loading, I generate voltage. Okay, so this, the top equation, is very useful as an actuator. The piezo acts as actuator. The bottom equation, the piezo acts sensor. Now, if we don't have any electric voltage, and so this is the regular material that is related by Hooke's law. Okay, the bottom material, the bottom equation, if we don't have stresses, it acts as Ohm's law. It's Ohm's law. Now, summary of all this. So, piezo material. Are governed by the following equations. Strain is equal to just want to add a couple of things here, so this will be all complete. We apply a voltage on this material in this direction. So the property epsilon is called epsilon 3,3. Okay. And if I want to look up the property in tables, I look this property when there is no stresses acting on the material. So I can put also on top of this T, when T is 0. When I look at the properties of the material as a mechanical material that does not have electric voltage on it, I can get the reciprocal of Young modulus at 0 current, or at 0 voltage. So this will be like this. So now the description is complete for a material working only in one dimensional. I relate the strain to the stress to the electric voltage. The top line is very useful for actuator, the bottom line is very useful for a sensor. Okay, now what we have is like this. In a matrix form, so if you look at the terms that I have now, I have the strain is related to the stress by the compliance. At 0 voltage. Okay. For regular material, that's all what we have. I can generate the strain by applying stress on the stiffness of the material or the compliance of the material. Okay, and usually these materials have 0 at this term. It does not depend on the electric voltage. If I apply electric voltage on a piece of steel, it will not expand or contract. The material of the steel will expand or contract only if I apply mechanical load on it, stress. The piece of steel, I can generate current through it by applying voltage, depending on this permeability term. I cannot generate current in the piece of steel by applying stress. So conventional material are like this. So in a matrix form, for conventional material. For this material, the off-diagonal terms are not zero. So it means the electric and the mechanical are coupled. This is not zero. So if I apply voltage, I generate strain. If I apply stress, I generate electric voltage. So now for a piezoelectric material, and the off-diagonal terms are the coupling terms. Between electric and mechanical. Between electric and mechanical fields. Okay, I just want to put a couple units here so you can there's this and then again here. One important thing is these materials are symmetric. The coupling terms between mechanical and electric is symmetric. So if I apply voltage, I generate strain. If I apply strain, I generate voltage. And the relationship is exactly the same. If I apply unit here, I can generate unit here. If I apply unit there, I'll generate unit here. If I reverse, I have reciprocity is reserved. So this is symmetric. Now here we have S11E. This is small s, D31, D31, and then epsilon 33T. Then we have stress and electric field. So the strain does not have any units. The stress has newtons, for example, per meter squared. The electric voltage, electric field, is we said volt per unit thickness, so it is volt per meter. So this now says S11E should have the reciprocal of this, so when I multiply it, I have no units. So this should be meter squared per Newton. D31 should have the reciprocal of these units. Meter per volt. Now the Displacement, electric displacement is so many coulomb charge per meter squared. Okay, so this unit has to be coulomb per meter squared, and it has to be also then multiplied by voltage. So this will be meter, volts per meter. I'm sorry, meter per volt. Okay, so this is unit of charge, units of voltage. So charge over voltage is units of capacitance. So this and this will be unit of capacitance, and capacitance is farad. And then the meter will cancel with the meter square. This becomes meter. Now the last unit, this unit, has to be like this. Has to be like this also. But this unit now, if I get it from the bottom equation, will be coulomb meter squared multiplied times meter over voltage. I'm sorry, stress units, which is meter squared per Newton. Okay, so this uses 2 coulomb per Newton. Now we'll go here on the sides. We know that the charge is equal to capacitance times voltage. The charge is also the integral of the current dt So now, if I take the integral of current dt and multiply it times voltage. So voltage times current is watts, so many watts. And this has units of watts times time, units of time, which is second. The watts is Newton meter per second times second, so this is Newton meter. So if I take the voltage and multiply times the charge, it has units of energy, Newton meter. Now we can come here and do this trick. I'll come here and multiply charge by voltage. Charge, I'm going to multiply it by voltage and divide by voltage. Okay? And then I'm going to come here also, multiply by meter and divide by meter. Voltage times charge has units of energy, Newton meter. So voltage times charge has units of Newton meter. And these will cancel out. And what is left is meter per volt, which is same as this. We're spending time on this because this is very important. Okay, now, after we said all of this, I'm going to take these two equations and manipulate them in a little different way. Any questions? Okay. Again, please rewrite these equations. And then now I'm going to take the top equation and divide by S1 1 and move this to the left-hand side. So I have the strain I'm going to write the second equation, and I'll replace the stress T by what we have here. And then we have the last term. Now, this is the compliance. When I take the reciprocal of it, will be Young modulus. This would be and then now this last term, I'm going to call it G 31. Then here we have D. And then if you look at, we have only S and E. So I have S here. And the term that multiplies S is D31 over this, which is exactly this term. So this would be G31. So I'm preserving the symmetry or the reciprocity. Now the remaining terms will be, I'm going to write them like this, minus, and everything multiplying E. And I'm going to take this term out. So this term is right here. And then now the remaining term is D31 squared. And the numerator is S11. Epsilon 33 and T. We can write this now as T is equal to Young's modulus S minus and then D. And then here we have G31 minus and this term, we'll just define it like this. K 3 squared K31, I'm sorry, squared minus 1. That's all what I'm going to say about piezoelectricity now, this lecture. I relate the stress with the strain. In the piezoelectricity, I apply electric voltage. I generate electric displacement related to the strain and electric voltage. Okay, now we go into what we want to do today. The augmented temperature field. I'm going to describe the viscoelastic material as follows. We'll go back to regular symbols now. Stress is equal Young's modulus, strain. Then I will relate this material to temperature as follows. I'm going to define a variable here, delta. Okay? And then I will define the thermal field like this. This is the thermal field. So now this G was property of the material, D31 over the S11. So this is a property of the material. So is this delta. Now here is the electric field. The electric field was volt per unit thickness. Now I'm going to describe it here as thermal field. Thermal field is voltage difference divided by thickness. Thermal field will be temperature difference divided by thickness, or thermal gradient, If you're doing conduction problem, you're looking at thermal gradient. So the thermal field is temperature gradient. Now let's look at the second equation. Second equation here, I was applying electric field. So I was applying electric field and I'm generating electric displacement. Electric displacement from the units that we had was charge unit area. Charge per unit area. The charge was the integral of the current divided by the area. Now the same story here. I'm going to apply, instead of electric voltage, I'm going to apply thermal field. And this is property of the piezoelectric material. Now I'm going to have here a parameter, property of the viscoelastic material. Very similar. I'm going to preserve the signs and everything. So I'm going to generate here exactly like instead of electric displacement, I'm going to generate thermal displacement. Thermal displacement. This is called affinity. This is thermal affinity. So now if we look at the relationship between E and D was like this. E, and then we have here the properties of the material system that we have here. So now in effect, if I apply temperature difference per unit thickness or temperature gradient, I'm going to generate the integral of the heat per unit area or thermal flux in the material. So you see what we've done. The last thing is straight forward here. We relate this to the strain, and as we've done here, we have symmetry or reciprocity. So this would be also done. The top equation is a mechanical equation. Now, we augmented this with a thermal equation. So the field, I added a parameter which is the field, and I augmented with the mechanical system. If you look at this equation and this equation are exactly the same. The parallel is exactly the same. Now from here we do a little manipulation, we'll come up with the storage modulus and the loss modulus for any viscoelastic material. This is also very powerful as the general model that we did for GHM equation. Okay. So the bottom line of all this summary, the ATF, a model which is the abbreviation of this augmented temperature field. Augments the dynamics of mechanical systems with internal temperature field in a manner similar to the general description of piezoelectric material. Okay. Now, in this latter case, we couple the mechanical system with the electric field, where mechanical and electric fields are coupled okay. Now, we're going to concentrate on this model now so we can generate everything on it and see how it behaves. Here, And if I take any piece of material and heat it, the temperature will change. The rate of change of the temperature is proportional to the heat that I'm putting. So this, I can explain it like this. Rate of temperature change is equal to some constant times the affinity. This is the rate of temperature change and the affinity, or the thermal flux. Rate and I know also that the rate of thermal flux is in the opposite direction of the temperature difference. The temperature difference, I'm going to say the temperature different from an equilibrium temperature. In the conduction problem, you have to have the gradient in the opposite direction of the heat flow. I have high temperature, low temperature. The heat flow from the high to the low. Temperature gradient in the opposite direction. So that's where the negative sign is. Now, where this equilibrium gradient occurs when A is equal to 0. From the bottom equation, then we have delta, and the strain will equal to alpha and zeta bar. So the equilibrium temperature gradient will equal to delta over alpha and epsilon. Now I'll take this and plug it here. And the result is minus B. B is a constant. We'll see its physical meaning when we get done. So now we have zeta dot will equal to minus B minus delta over alpha and epsilon, or an epsilon. I'm going to call this equation equation 1. This is equation 2. going to say now for sinusoidal loading. I have the stress, sigma 0, e to the I, omega t. And the strain, epsilon 0, e to the I, omega t. Now if I come here, and I put this exponential sinusoidal, then the result here will be the same, okay? So this would be also I'll take this and plug it these equations. Let's take the equation 2. So we have I omega plus B times e to the I omega t times zeta naught will equal to B delta over alpha epsilon naught e to the I omega t. And I'll cancel the I omega t between these two. Then I can eliminate zeta naught and replace it by B delta over alpha divided by I omega plus B epsilon naught. Now we'll go in equation 1. I'll do the same. I'll plug in these. So we have sigma 0 e to the I omega t will equal to EU epsilon 0 e to the I omega t. Drop the I omega t from all of them. Then we'll have sigma 0 EU epsilon 0 minus delta. And then instead of zeta 0, I'll replace it from here. So now this will be B delta over alpha epsilon 0. Now we're done. We have here a relationship between sigma 0 and epsilon 0. And this relationship is EU minus B delta squared over alpha divided by this term. So this term I'm going to multiply it by the complex conjugate, numerator and denominator. So this will be minus I omega plus B divided by omega squared B squared. Now we have part real, part imaginary. Then this now will be our E asterisk epsilon 0, and this is made of two components, E prime and the E prime is the storage, and this eta is the loss factor. We can clean this and put it in this form. Take all this away. Now the nice thing here about this now, if you have this viscoelastic material and you come and put inside the viscoelastic material piezoelectric powder, then you can come to these two equations and add electric voltage. The viscoelastic material with piezoelectric powder is very important coating for submarine hulls, okay, or anything that you want to reduce sound radiation from it. So you can model it with electric voltage, thermal field, and strain. And this viscoelastic material will have all these parameters combined together. Now these final results, E prime will equal to ER, not EU, 1 plus delta omega over B squared. This is divided by 1 and eta will equal to delta 1 plus delta omega over B squared, where I defined two new things now. ER is equal to EU minus delta squared over alpha. And this comes from here. If I take in this equation omega and put it equal to 0, this term will disappear, this term will disappear. I have B squared, cancel with B squared, and this will be left EU delta squared over alpha. So this is in effect the storage modulus at frequency omega is equal to 0. Then the second term that we defined is the delta, and this delta will equal to delta squared alpha over ER. Now the rest is exactly like what we've done before. I like this model and it works fine. If it doesn't work, then we come here and make summation, okay? And this summation will be for different i's, I, and I. The main man that done this work is George. Monsieur. Slessy Autre. So don't make mistake because French name. And he's done many papers in this area. That was his PhD thesis from UCLA. And so we have parameters that we want to identify. I made examples only if I have two parameters. If I want to have two terms. Oops, I'm sorry. So I used this equation, and I have two terms. I is equal to 2. I have two terms. So I have 1 plus this term for 1 plus another term for 2. Okay? We have to keep in mind the constraint that we have. When omega is equal to 0, this term will disappear completely. And the first term will be at 0. ER will be the Young's modulus at 0 frequency. When omega goes to infinity, I divide by omega squared as we did. This term with this will be 1. This term here will be 0. And then I'll have 1 plus delta times ER should equal to ER at infinity. So I have constrained that this cannot just be any number. It has to be this plus this times this should be E at infinity. Okay? So now, if you look, this would be exactly what I described last lecture for the other case. I took the same material, the storage modulus, the loss factor, get maximum and minimum, and then now I have the storage modulus and the loss factor from these two equations. Now here, x1 is delta. x1 is delta 1. x2 is b1. Delta is x1. b1 is x2. Now I go and write the same for the loss factor. Get the errors between the predicted and the measurements. Put the constraints. All these numbers have to be positive numbers. The B and the delta. And then now I have to put the constraints that at infinity I have to have the sum is governed by this equation. Now I go and get the optimum parameters, which is the second equation, the second chart will give us now the optimum parameters that I have from the optimization. And the optimum parameters in the handout are the last page. The last page in the handout. That's how I generated these parameters. Now I put them in, and I have two mini oscillator, ATF mini oscillators, predict these numbers and plot them again as experimental results. This is the output. I'm happy with this, fine. I'm not happy, put one more, put two more. As we've done in the homework, you can make these exactly collapse on top of each other. Okay? So after today's lecture, you have enough investment in the course. This is super coverage of viscoelastic material. What we need now is to add this to a structure with finite element so we can know how this whole thing goes together in a finite element description. Okay? But what we covered so far is a very nice coverage of all the different areas and how it progresses from one step to another step to the last step, which where we are now. Next lecture, we'll combine this with finite element so you can see it in a case of a rod. And then the extension for beams and plates is very straightforward after this. Fine, have a good weekend and we'll see you next week.
Okay, so
Easton?
yeah.
Very tough. But, Jesus Christ was $10. Yes, sir. try to wrap this viscoelastic damping. And the last thing that we will do is modeling. For what we've done so far, we just model only the viscoelastic material. Now we will model it with the structure. Modeling viscoelastic material slash structure using finite element method. I'll use here, we'll model the viscoelastic material using GHM model of method. But the same approach applies if we use other methods. Okay, and I'll begin first, number 8, looking at a rod slash, we'll just say rod first. So the people that took the vibration class, I'll take a rod and divide it into elements. And I'll take one element, and this element has a node at one side, node at the other side, and then we'll place local coordinates in the rod. Okay, the rod will oscillate in longitudinal direction by u. So this is, for example, element 1, and then this is element n. And we will consider any general element. Now for this element, I will say the u at any position is equal to a1 plus a2 and x. And this would be my shape function. And where the a1 and a2 will be determined in terms of the nodal displacement at ui and uj. In terms of ui and uj, and these two are the nodes that bound the element, where I and j are the nodes bounding the element. And this case is also, this is one-dimensional case. Now, at x is equal to 0, the u will be the u of I, and when we plug in x is equal to 0, so this will equal to e1 and then at x is equal to L, U will equal to Uj, and this will equal to A1 plus A2 and L. And from here, I can write down Ui, Uj in matrix form is equal to A1, A2, 1, 0, 1, and L. And then now I determine A1 and A2. And this will equal to the inverse. And here Ui and Uj. We solve for this and plug in here. You'll see that U will equal to 1 minus x over L, x over L. I'm sorry, before we do this, let me just so we can see where it comes from. So now we can say, but U from the shape function, I can write it as matrix form. A1 and A2. And then now I'll replace A1 and A2 from here. So now this will equal to 1 and x, and then 1, 0, 1, L inverse, Ui, and Uj. And then now this will reduce to, when we do all the calculation, this will become 1 minus x over L, x over L, Ui, and Uj. So now I'll take this here, then we can write U is equal to some matrix vector n and some delta vector. We'll see here where the n is this 1 by 2 vector, and the delta is the Ui and Uj. And this is our nodal diffraction vector. Of course, here I can expand this equation, and this will equal to 1 minus x over L U I plus x over L U J. And you could see here, if I put x is equal to 0, the second term will drop, and it will be U will equal to Ui. When x is equal to L, the first term will drop, and the last term will be Uj. Okay, so now this satisfies this. This is my equation for driving the finite element. And the n will be my interpolating functions. So now I want to write down the description of the finite element. Then we'll put the potential energy, kinetic energy of the element. The potential energy is equal to 1/2 the integral over the element of E A and then u of x squared dx. And of course this, I can write it like this. This is partial u by partial x, which is the strain. The strain times Young's modulus is the stress. So this times this will be the stress. And this term is the strain. So this equation is equal to 1/2. And I'll take the area out. And then I have the integral stress times the strain times dx. Or leave A inside in here. And the integration between 0 and L. So now this stress times the strain times the volume is the energy that we have in the element. So this would be my potential energy. So what we will do, we have expression for u. I'll replace it by the partial derivative. This term is the only term that depends on x. So I'll replace these two from here. And then we extract the stiffness matrix. So now here, but u is equal to m and delta. Then u of x is equal to the partial derivative what we have with respect to x, and this will equal to partial derivative with respect to x. This will equal to 0, I'm sorry. So this will be minus 1 over L, and the second term will be 1 over L times the delta. Now I want to calculate the this term, the one we have inside here. So now the potential energy will equal to 1/2 the integral from 0 to L. EA, I'm going to put them outside. And I'll make this 1/2 here. And then we have dx here. And I'll replace u of x by this matrix, which is 1 by 2. Times this delta. This delta is the nodal deflections. These are fixed, so they are independent of x. So I'm going to take these out. So we have done from one of these. Now I'm going to put the second one. This is a scalar value. Scalar value. So I'm going to put another scalar value. If you look at the vector here, this is 1 by 2. The delta is 2 by 1. So this is a scalar. So I can write a scalar like this, or I take the transpose of a scalar, still a scalar. So the transpose of this will be minus 1 over L, 1 over L, and then delta transpose. Okay, now, so now we're done. So we have 1 over L. I'll factor 1 over L from here, 1 over L from here, so I have 1 over L squared. So I have EA, L squared. And then this would be the integral from 0 to L. This would be 1 minus 1 minus 1 and 1 dx. I have here transpose and 1/2. And then now I do the integration of all of these elements. So we have here the potential energy will equal to 1/2 delta transpose EA. And then when I do the integration of any of these terms, this would be X between the limits, so it becomes L. I'll factor out one of these L outside, so I'll have here EA over L, and then 1 minus 1 minus 1 and 1, and delta. And I can rewrite this as 1/2 transpose, and then replace all this by stiffness matrix K. Okay, now we'll say here where the K is the stiffness matrix. This is now equal to EA over L, 1 minus 1 minus 1 and 1. We've done this in the vibration class. Okay, now what we want to do today, instead of this, I want to do rod and viscoelastic material. So I have the rod like this. Again, I'm divided into elements. And for now, for today, I will only describe this case. The rod is fully treated with viscoelastic material. Okay, and then now I'll concentrate on this. This is I and J. And then now, instead of just one uniform material, I have this complex or composite material. It is symmetric, everything is symmetric around the center, and I will use the same expression for the shape function. I will have the same final form for the interpolating function. Now what will be different is now here. I go calculate the potential energy. Potential energy now is the energy that I store in the components of this composite rod. I have the main base or parent structure plus the energy that I store in the viscoelastic material. Unfortunately, for the structure, this is real part. For the viscoelastic, I'll get exactly the same thing, but this is now the one that I have to express either by complex number or by GHM or by ATF or whatever method that we want. Okay? So now, for the rod slash VM, I have also, I can write U as M and delta. Delta is U at I and U at J. When I come here and I pull this material is bonded to the structure. When I pull, both of them will move with the structure at the same displacement. For now, after I finish next chapter, which is the piezoelectric material, and I go to the following chapter, which is the constrained layer, then the story will be different, and I'll just say this is called unconstrained stiffness on the side. For constrained VEM, I'll have something like this. Now we have VAM here. I have my base structure here, or parent structure. And that's the structure that I want to damp its vibration. So what we do, we will put viscoelastic material. And then as we will see when we get to this, we'll see that if we use this arrangement, then we'll get much, much better damping than this arrangement. Because now I come on the viscoelastic and bond on the top side a constraining layer. So now what will happen is I take the parent structure and stretch it, or compress it. So the parent structure can be, in one case, let me okay, now I'll come in the main structure and stretch it, for example, by this much. So what will happen? The layers of the viscoelastic material that are bonded to the structure will stretch with it. So the viscoelastic on the structure will stretch. I'm putting all the excitation on the parent structure. So I stretch the parent structure. Because the stretch is done dynamically, this will get the first elongation. But by the time it gets into here, it will take some time, phase delays. This will not stretch as much as this. It will stretch a little. Okay? The layers of the viscoelastic material bonded to the top constraining layer move with it. So they move up to here. So now what will happen to the viscoelastic material? It will look like this. It will shear. The viscoelastic material will shear. Here, when I pull the two ends, the viscoelastic material stretches. Here it shears. The mechanism for elongation gives very small damping compared to the mechanism of shear, as we will see why. Okay? So now, in this case, the main mechanism, when we apply forces here, is the shear mechanism. In this case, the mechanism is longitudinal stretch. Okay, and of course, if we reverse, the structure has to go through cyclic oscillation. So the structure, instead of stretching, it will contract. When it contracts, it will be smaller than what we have on the top. But the top, by the time the contraction comes to it, it is still long. And then the viscoelastic material will shear in the opposite direction. So this is okay, so the constraining layer, the main purpose of it is to transfer the damping mechanism from a longitudinal damping mechanism to a shear damping mechanism where the damping is much higher. So the constraining layer changes the damping from longitudinal damping as in case of the unconstrained EAM to be more efficient shear damping. And this we will describe in great detail why it is more efficient than longitudinal damping. Okay, of course, we could make the top layer active constraining layer. So the active constraint layer, when I see this is stretching, I can make this shrink more. So if I take the top material and instead of just any material and I make it piezoelectric material, take the structure response, feed the signal to the top, I can make this more effective. Because the whole idea is this shear angle. I want to make this shear angle as large as possible. So now, originally I was here. Now if I take this and feed it back here, I can make this shrink and take this position, and I can make the shear angle very big. And this is what we done in active constrained layer damping. I can make it active. We will not describe this in this class. Okay? So with unrestrained viscoelastic material, and I pull it, the structure and the viscoelastic will move the same distance. So all what I need is one displacement here, because this displacement will be of the structure and of the viscoelastic material. Same here, one displacement. In this case, I have displacement of the structure, parent structure, and displacement of this. So I have to have more than just one description at one end, and more than one description at the other end. So this equation will be still valid for the case of the unrestrained viscoelastic material. And this nodal deflection vector still Ui and Uj. And this is still the same. 1 minus x over L and x over L. These are two entries of the vector. Now the potential energy. Potential energy is the potential energy of the parent structure energy of the viscoelastic material. What I'm going to write here is not 100% accurate. It's not 100% rigorous, but I will get to the same result, okay? And then later on we'll tell you why. Okay? Because the structure, it's potential energy, because whatever I give, I'll get back. If I write the same thing here for the viscoelastic material, whatever I give, I will not get all of it back. But we'll say, for now, I don't know what this viscoelastic material will do to me. Okay? We'll just say it is just a material, I'll treat it as a base structure. I can write this potential energy and kinetic energy of them as if they are regular material. And then we'll write down Lagrange, for example, get the equation of motion. Or I can write potential energy, kinetic energy, and dissipated energy in the viscoelastic material. Then I can write down Hamilton principle and generate from it the equation, or I put in Lagrange the non-conservative term, which is the damping. But the two will lead to the same result. So for now, I'll just do this quick and non-rigorous way. Okay, so now our potential energy is potential energy of the structure, potential energy of the viscoelastic material. So this will equal to 1/2 integral E S A S. This is structure. And then U of x dx squared plus 1/2 integral E viscoelastic A viscoelastic. Viscoelastic strain exactly the same as the base structure. So now I'll put this U of x squared dx. Now I have the U, then I can replace the U of x by the interpolation function. Then also U of x will equal to and then I repeat exactly what we've done before. So now here, then the potential energy of the entire system will equal to, do here the delta transpose, and then integral ES, and then we have NX transpose, NX dx delta. And then I go in the second term for the viscoelastic. 1/2, the same story. Transpose NX dx and then delta. And if I say the material distribution and the geometric distribution are uniform, then I can take this outside the integral. So now if I do this, then I have 1/2, and I'll take this outside the integral. And I'll take this outside the integral. All the remaining terms are exactly the same. So I can factor these out, and I'll have E structure, A structure, E visco, A visco, and then let me put here delta transpose, and then 1/2, and then we have integral N of x transpose N of x dx and delta. And then now, instead what we had here, the integrations will be exactly the same like this. Exactly the same. The only difference now, instead of one material, I have the total longitudinal rigidity of the composite. Structure and viscoelastic. So now this will give me the stiffness matrix of the composite material. 1/2 A composite, and then good. And the final result will be K composite will equal to E structure, A structure, E viscoelastic, A viscoelastic. For the mass matrix is very simple from the kinetic energy. Also, the kinetic energy, this will equal to 1/2 the mass per unit length, okay, times dx. This will be the infinitesimal mass times the velocity squared, u dot squared. For the entire rod, I'll integrate from 0 to L. Now let's write it down. So this will be 1/2 u dot squared. The mass per unit length, I'm carrying with me, if I take an element here, dx, and this is dx. So when I look at this element, I'm carrying the parent structure and the viscoelastic material. So this will be rho structure, area structure. Rho is kilogram meter cubed. The area is meter squared. So this is kilogram per meter or mass per unit length. So the mass per meter is rho as times dx. So this is the mass of the parent structure plus the mass of the viscoelastic material. Now the rest is straightforward. I want to calculate from here the mass matrix. We'll say here now, but u dot is equal to, I'll use this equation, interpolating equation. U dot will equal to, the first matrix is a space-dependent matrix. So it does not depend on time. The last matrix is the nodal points, they move back and forth with time. So this is the derivative with respect to time. Now I take this and plug it here. Then we have the kinetic energy will equal to 1/2. Same story as we've done. This will be delta dot transpose integral from 0 to L. Take also these out. Rho S AS, rho V AV, and the inside will be N, not NX, transpose n dx, and then delta dot. And this will be my mass matrix of the composite. And if we do the calculation, then the mass matrix will equal to rho S AS rho V AV, all this times L, and when we do the integration, this will look like this, divided by 6, 2, 1, 1 and 2. The stiffness matrix is like what we have at the end here. Okay. So now I can write the equation of motion of this system. Equation of motion. So it will be M. And then now my vector for the nodal deflection is ui and uj, with this will be in the Laplace domain s squared u1 u2 plus the stiffness matrix u1 u2, and then this will equal to the force at I, force at J. Now, the M, I can replace it from here. Rho S A S rho V A V divided by 6 times L. And then we have 2, 1, 1, 2 S squared U1 and U2. This has no problem whatsoever. The density is real, the area is real, this is real, real. Everything here, no problem. Plus, now replace the K from here. And the K from here, I'm going to do it like this. First, E over L, 1 minus 1, minus 1 and 1. The second term is the second term is the problem is. So now the second I'm going to write it as C. Yeah, sorry. Here, U1, U2, plus. Second term will be this, 1 minus 1, minus 1, 1. U1 and U2. Now everything here is also real. Or does not depend on frequency. Does not depend on frequency. Everything here is also real and does not depend on frequency. Or temperature. Maybe a temperature on the density, but very little. So this is real. And independent. Or temperature. Maybe a temperature on the density, but very little. So this is real. And independent. frequency. And this term is not. This second is not. So now we do this second term. So I'm going to write it like this. We have here A or L. 1, 1, minus 1, and 1. U1, U2, phi, FJ. Now the problem is in this Young modulus of the viscoelastic material. So last time we said I can possibly write it if I use this method like this. E viscoelastic 0 of the viscoelastic material. So last time we said I can possibly write it if I use this method like this. E viscoelastic 0. And then 1 plus alpha 1 S squared twice zeta 1 omega 1 S squared twice zeta 1 omega 1 S omega 1 squared. For example, I'm going to do the derivation for this case today. Okay? And then the homework you will do if I put summation here. Okay? It will be exactly the same. Okay? So now I can take the U and multiply it times this term. And the same story, multiply times this term. Okay? Now, from here, I can break this down to one more step. Here, so I have here this, and here I have this. And now, I'm going to break this down one more step. This step has EV0 times AV over L times this. Plus the remaining term that depends on the omegas and the alphas and the zetas and so on. So this would be alpha 1 EV0 AV over L times the S squared and then the matrix 1 minus 1 minus 1 and 1 U1 and U2 and then phi and FG. Now if you look again, this term stays as it is real. This term is real. This term is now real. Because if you remember, AV0 was the minimum value at zero frequency. Now this term is the only term that is neither real nor independent of frequency. It depends on the frequency, and because of the S, it is also not real. Okay? So now if you look at this term, and this term, these are exactly the same. EAS over L real of the structure. EV0 is real for the viscoelastic. A viscoelastic over L. So now in effect I have these two multiplied times the summation of this plus this. This is real. And then I have the problem at the last term. The last term, we'll do coordinate transformation, add the internal degrees of freedom Z1 and Z2, for example, for the viscoelastic material, and then augment it with the structure and get the equation of motion. Now, we have to keep in mind, I did this with one mini oscillator. One mini oscillator. Okay? For one mini oscillator, my structure has 2 degrees of freedom, U1 and U2. When I operate with this on this, I will end up with Z1 and Z2. So my structure has 2 degrees of freedom. My mini oscillator now has 2 degrees of freedom. In the example that I gave you last lecture, I had structure with 1 degree of freedom, and I added 1 degree of freedom. So now we have 2. Then we double, becomes 4. Now if this is 3, then I have 3, so it becomes 6. The size mushrooms. As you increase the degrees of freedom, the size mushrooms. Now if I have 2 of these, 2 summations, then things become horrible. Okay? Now, how we reduce this to a nice clean form. I'm going to rewrite this equation now like this. In a compact form. I will have m s squared, and then I'm going to write x as my nodal vector mu. And then plus this K, you remember, was made of the structure and the viscoelastic material. So this is the structure, and then the viscoelastic material, and then we had this matrix, and then x, and this is equal to f. I'm going to simplify this one more time like this: ms squared x plus es over L, and I'm going to call this K bar. It's not stiffness matrix, but it looks like a stiffness matrix. I'm taking only this matrix and I'm putting in K bar. So this is K bar times x plus this is now is E V 0 A V over L times 1 plus this term. And this term, I'm going to just call it a general name, some function h of s. And then the K bar, and then the x, and this is equal to f. And again here, where the h of s is the alpha 1, and add it to this term. So now we have m s squared x plus e s a e b0 a s over L plus ES over L, okay, plus E B0 AS over L and H.
Hello? AB, TV is over AB.
I'm sorry. AV. AV, okay. And then we have K bar X is equal to F. Okay, now I'm going to factor this matrix out. This is ms squared x. I'm going to factor this out, ES EV0 AV over L. And then I have 1 plus EV0 AV divided by ES AS EV0 AV times H is equal to F. And then now, this approach applies to rods, beams, whatever. In case of the beams, this will be EI, EI, and so on. Okay, so now this will be, I'm going to call this E total over L. And then we have here 1, and then this EA divided by summation of EA. So this is dimensionless term, and I'm going to call it the ratio R times H K prime X is equal to F. If you look from here, the EA total is this term plus this term. And then now here, this is the H term that we have. Now I'm going to take here a little note on the side. On a side note. And on the side note, we'll say, let, for example, H x is equal to alpha x minus z. X, in my case here, ui and uj. So z is the internal degrees of freedom of the viscoelastic. It will be same size. Okay, now, I'm going to say this, let this would be the case, okay? And then I have 0, and let this will be like this, alpha plus alpha squared, oops, I'm sorry, alpha 2 zeta over omega, S and Z, plus alpha z minus x. Now, from here, if I combine these two equations, then I can replace this term by hx here. Then this says 0 is equal to alpha omega squared s squared z alpha twice zeta over omega sz, and then this term is equal to this term, so it will be minus this term. So I'll have here minus h x okay, and this is equal to 0, hx. Okay, now I'm going to clean this, and I have hx on one side, and zs and I'll multiply both sides by alpha squared, by omega squared. So I have omega squared hx is equal to sz omega 2 and then alpha plus alpha s squared and z, or I can factor the alpha out from here, and the z we'll have like this. Or from here I can write z alone is equal to before we do this, can do it like this. And then now here is equal to omega squared, and I'll replace h by what we had for h, which is alpha s squared and then x. This is h. And then I have here z, alpha, now if you look at this equation, I can drop this term and this alpha with this alpha and this term, and this will give us what is left on the left hand side is z, and what is remaining on the right hand side is omega squared and this equation, if you remember from last lecture, is the transformation equation that relates the degrees of freedom of the structure with the internal degrees of freedom of the viscoelastic material. And this is the degrees of freedom of structure. So the purpose of this side note, last lecture I gave you this equation so I can combine the viscoelastic material with the main structure by adding these internal degrees of freedom to the structure degrees of freedom. This equation, I can rewrite it in this form. I can rewrite it in this form. These two equations are exactly this equation. Why do we write it in this form? Because I can multiply here by E V0 AL and K. Both sides, and then we can combine this with the structure equation, get the entire final form of the finite element of the system. And I'll do this next time. You were saved today. because I had the programs and nice homework. But okay, so I'll see you on Thursday. So we'll continue the last topic that we were talking about was finite element modeling of the structure viscoelastic material. And we ended up with these equations. We found that we have here, this is the mass matrix of the structure. And it's very important now, and I'll say I'm talking about an element. Okay? Oops, I'm sorry. Element equation, because my structure can have many elements, only maybe one or two are covered with viscoelastic material, because I don't want to cover everything with viscoelastic material. You cannot, okay? So our structure is like this, and we only have a small portion of the structure covered by the viscoelastic material. In this case, it's unconstrained viscoelastic material. So maybe I can divide this to something like this. So I have element 1, 2, 3, 4, 5, and 6. Okay? What I have here is the equation of motion of one of these elements. Because each one of these elements has the structure and the viscoelastic material. These elements, we already done them. We know how they are. But then I have to assemble everything after I'm done. Okay? So the element that I'm talking about here is an element of the structure of viscoelastic assembly. Okay? And again, this is the way to do it. You know, like you cannot put viscoelastic material everywhere. Viscoelastic material adds weight, and you have to minimize the weight. So in many applications, like maybe I've showed you the drill that we did for Black & Decker. You cannot put viscoelastic material everywhere because this will raise the price maybe 50 cents. They will not, they don't want to buy it. Okay. Same for cars. We did project for Fiat. They want only $30 worth of viscoelastic material, no more. So the car is $10,000, but you can only put $30 viscoelastic. So you cannot put it everywhere. Lexus, for example, has viscoelastic everywhere. Okay, but you pay the price. If you look at the door of the Lexus, and maybe like 1 or 2 years ago when the Lexus was just coming in the market, they used to have a commercial with a guy playing the drums on the door of the Lexus. And it is dead because the door is made of 2 sheets and in between them there's viscoelastic material. You cannot afford it in little VW or Fiat, okay? So in any of these little products, that's where engineering comes in. You have to place the minimum viscoelastic material to get the maximum benefit. So we have very small viscoelastic material on the entire structure. What I have here is an element that has structure and viscoelastic material. So this is the mass matrix of the assembly. And again here, this we wrote last time, AV0, because this is the minimum. And then now this H is what we described by a GHM model. And H was equal to alpha S squared and if I use one mini oscillator, then these are all ones, 1, 1, 1, and 1. And the K prime, if you remember, for example, for the rod case, this K prime, I said it is equal to 1 minus 1 minus 1 and 1. This is equal to my K prime. Okay, so that's where we stopped the last lecture, and then we added a little thing. This is number 1. The second thing that we've done is look at some identities. And the identities we said will use the transformation Z is equal to omega 1 squared squared This transformation relates the structural degrees of freedom to the internal degrees of freedom of the viscoelastic material. So this is the internal degrees of freedom of the viscoelastic material. And then this is the structural degrees of freedom. This is what we did when we start looking at GHM model, and we described this equation along with the structure equation, and from it we extracted the physical meaning of any of these parameters. Okay. Now we said that this is equivalent to the above transformation the following equations. if I take this equation and replace it here, we can show that the final results gives us this equation. That's what we start the last lecture. So these two equations, if I replace or eliminate this parameter between these two equations, then I end up with this equation. So everything that we said on GHM model is fantastic. Now why we've done this, I'm going to take these because I have here H and then I have X. So I have H and X. This is H and X. I'm going to multiply these H and X by K prime times this. Both sides. And two equations. Multiply equations 2 and 3. And this is 2, 3. By I'm not going to multiply yet. Okay, leave this for a minute. I want to clean this equation so we can multiply intelligently. So equation 1 can be rewritten as m s squared x plus as over L, EV0 AV over L, okay, plus EV0 AV over L times H, and then everything is multiplied times K prime times X is equal to L. And then I'll factor out this term from the bracket. And this term is the structure plus the viscoelastic at zero frequency. So this will be the total stiffness of the assembly. So this first term is, we'll call it ET, a total stiffness of the structure viscoelastic material at zero frequency. Because this H, if I replace each S here by I omega, so this is depending on frequency and frequency. So when frequency is equal to 0, H will go to 0. So at 0 frequency, this would be my stiffness. Okay? And now I'm going to do one more step here. I can rewrite the same equation. M S squared X E total A total over L, and then this is 1. And then I'm going to call this ratio between longitudinal rigidity of the viscoelastic to the total sum. I'm going to call it ratio R H K prime X equal to F. And here where R is E viscoelastic, A viscoelastic over E structure, A structure, viscoelastic A to B. Now the final equation, we have m s squared x plus E total A total over L 1 plus R H A prime X is equal to F. So now I'll come to equation 2 and 3, multiply equations 2 and 3 by this multiplier. And I'm going to multiply it by R K prime. So we have R H K prime X will equal to R H K prime alpha X minus Z, and the bottom equation is 0. Yes, sir.
You get an extra H on the right side.
Yeah. Okay, so the bottom equation will be alpha R K prime over omega squared S squared Z plus alpha R K prime twice over omega S Z plus R K prime alpha Z minus X. Yeah, I don't need all these anymore. Call this 4 and 5, and I'm going to put these in a matrix form. So we'll have R K and 0 and X and S squared X and Z, another matrix S X and Z, and then another matrix X and Z. So the first matrix is done. The second one, I have only this term that's depending on the S squared. There's nothing for the X, so this is 0, 0, 0. And this is alpha R K prime omega squared. The only term that depends on the S is associated with Z, so this is 0, 0, 0, And this will be twice alpha r k prime over omega n. Okay? And then now, the last term, I have x and z here, and I have x and z here. The first term is rk alpha times x, and then minus z. And then here's the reverse. So this will be r k prime alpha, and then this would be 1 minus 1, or identity, minus identity, minus identity, and identity. Okay, now we don't need this. Let's see here, but m is squared x plus p total over L times k prime x plus p total over L R k prime x is equal to f. Now I have this term is right here. Is this term. So now I'm going to replace this term from the top equation and reduce the equation of motion from what we have here. So now this, let's call this equation 5 and 6. And let's say now here combine. 5 and 6. So when we combine these, this will give me m 0 0 and then this will be alpha R, and this is K divided by omega squared S squared X Z plus 0 0 0 twice alpha zeta R K over omega S X and Z plus 1 plus alpha R minus alpha R minus alpha R and K X and Z, and this is F and 0. And I'll say here where K is equal to E GAT over L times K power. Okay? Now, this is super important now what I'm going to say. This K is equal to some constant times K bar. Times K bar. This K bar is this matrix. For example, and the rod and the beam will be 4 by 4, but both of them have unique characteristics. This is a singular matrix. This row is exactly this row times -1. Okay? So this matrix is a singular matrix. Now, I know that this matrix is not singular matrix. The mass matrix is not, because if in the rod case, it was 2, 1, 1 and 2. Okay? But the K matrix is a singular matrix. Okay? This matrix is a singular matrix. Everything here is multiplied by a singular matrix. So now, the degrees of freedom of the system depends on how the system is assembled and restrained. The degrees of freedom that we have in this simple case where I have single element, I have one deflection and another deflection on the, for example, if we take this element 4, this is node I and node J. So this is the deflection of these 2 points. Now let's say if I just have one structure that's made of one element of a structure and viscoelastic material. So if I take this and roll it like this, and I have viscoelastic, and I represent this by this equation, the stiffness matrix of this element is singular matrix. The stiffness matrix is singular matrix. So now what I've done is the structure as it is, if I don't anchor it to the foundation, it will move. So it will have rigid body degrees of freedom. Okay? This rigid body degrees of freedom, which are associated with the physical degrees of freedom of the system, they are transferred, because the K is singular, are transferred to the internal degrees of freedom of the structure. Okay? So this is singular and singular. So now this system of equation, I cannot solve it. Because this system of equation, I have singularity, singularity, and singularity. So now before I do this, I have to impose my boundary condition of the system. Because if I don't, I'm transferring the singularity of the original system to the viscoelastic material. So now I come here and I say restrain the system. So be sure that the system is anchored in place. Okay? Now, I'll just write down here, this is super important. Now where M and K are restrained matrices of the element. Or we can say, if my element is now, for example, it is a flying platform, like we said rocket, for example, or any space station, it is unrestrained. I want to make this work, I have to take the 0 degrees of freedom, the 0 frequency degrees of freedom, or the rigid body mode out of the stiffness matrix of the system and the mass matrix. If you don't do this, nothing will work. Okay? So, for us on ground, I have to restrain the structure. This is equivalent to, or eliminate, and we'll leave space here, the rigid body modes from the matrices. And here we'll say eliminate using, for example, static condensation or Gaussian reduction. This is super important. In the paper that was done originally by Gula and Hughes and McDavidge, they have done this by some transformation. But I don't need this for our application. I'm going to restrain the degrees of freedom of the structure. So K and M are non-singular matrices. The degrees of freedom of the internal damping are actual degrees of freedom. They are not duplicate. For example, if you look at this K, it has rows and columns. The rows are repeating. So this means if I have 2 degrees of freedom structure, I have 2 degrees of internal damping. So this means I'll have also 2 rows here that are linearly dependent. So the matrix is singular. Okay? So now based on this, we are done. We can program this and look at the response of the structure. If I have many of these, so I'll have several of the alphas, several of these, and then I'll have summations as we've done in the previous classes. Okay, so what we have here, we have a structure which is aluminum. And in the viscoelastic material that we have, please write next to this the data that I gave you for the diad 606 were shear modulus. Shear modulus. So the shear modulus and I gave you the data in pound per square inch. Now I want to transfer this because I have a rod going in longitudinal vibration, so I need Young's modulus. So Young's modulus is related to the shear modulus by this equation. Young's modulus divided by 2, and this is Poisson ratio. For viscoelastic material, this number is almost 0.5. So I have here 0.5 plus 1 is 1.5 times 2 is 3. So this says Young modulus is equal to 3 times the shear modulus. Now I want to get Young modulus of the viscoelastic at 0. So this is 3G 0. Or we called it in the class 3G minimum. So now this number is 3G minimum. And then I convert it to Pascal. The pound per square inch you divide it by 14.7 and then multiply by 1 e to the 5. Or approximately you multiply times 7,000. Okay? So now we have the Young modulus of the base structure and of the viscoelastic material. This number, EV, is not EV total. It is EV0. EV0. Okay? Then now I have the rod has 1 centimeter thickness and 1 inch wide. So the rod is like this. So this is 1 centimeter, 1 inch or 0.025 meter. The thickness is 1 centimeter or 0.01 meter, and the viscoelastic I think was 0.025. 0.025 meters. So now I can calculate the area. The area is the thickness times the width, the thickness times the width. And then I have the densities of the aluminum, of the base structure, and of the rho V, okay? This ratio is wrong here in my handout. In your handout is correct, and this transparency is wrong. In the handout, the ratio R is like what we define it on this board. R was EV0, AV0 divided by the total. By the total. So this is E total, A total. That's what you have in this handout, okay? Now, I put the GHM model with single mini oscillator. That's the number that we had from before. If you remember, when we did the optimization, this was the alpha and the omega 1 and the zeta 1. Now I define E as 1, ZZ as 0. And then I have factor for the structure, factor for the mass matrix. This number is the factor for the structure. The mass matrix, if you remember from last lecture, was equal to rho structure, A structure, rho viscoelastic, A viscoelastic, this whole thing times L divided by 6, 2, 1, 1, 2. So this factor is factor of the mass matrix. So the factor for the structure is the total longitudinal rigidity, E times A. E times A of the viscoelastic, E times A of the structure divided by L, and then for the mass, density times area. Now I put the stiffness matrix of the element. So this will be factor times 1. Second element, the K prime is minus 1. And then I have symmetry, and then I have the corner element is factor times S. Okay? So now this is the stiffness matrix. It's the multiplier times 1 minus 1 minus 1 and 1. For the mass matrix, we have it here. Factor M, 2, and then I have this and this. Okay? I cannot leave these as they are. Now I have to impose the boundary condition. Before I do anything else, impose the boundary condition, I have one node is grounded. I and J. So now I take the row and the column and eliminate them from the stiffness matrix and the mass matrix. So this is the final result. I take this row, which is corresponding to U1, and this column, which is corresponding to U1, and eliminate them. I impose the boundary condition. The same for the stiffness matrix. So I only have element 2 and 2. That's element 2 and 2 for the mass and the stiffness matrix. Now I have them. I go and generate this matrix. Generate all this. The mass total is the mass and then 0. And then 0 and then alpha. R divided by omega 1 squared times K. Okay? So that's the first one. And then so on and so on. Now I have all this. Then I want to calculate response, frequency response. This structure has damping in it. These matrices, all real number. All real number. I can do time response or I can do frequency response. There's no imaginary. There's no imaginary here. So I can do everything in frequency domain or time domain. So now I did frequency response for this structure. And I did the same if I don't have any damping. If this viscoelastic material, it is there as a dead weight, it does not have any damping. No damping, undamped case. So I have the mass matrix and the stiffness matrix. And then I do the frequency response. The result is right here. The undamped is very high. Then this damping is longitudinal damping. You drop this much. In 4 or 5 lectures, I'm going to put on top of this viscoelastic material another layer to constrain its motion. You will see this number drop all the way down here. Okay? Because shear damping is more effective than longitudinal damping. Okay? I've done a fantastic job in this viscoelastic damping. So your reward is very nice homework, so you can exercise all this. So you can enjoy now viscoelastic damping. You know everything you need to know about viscoelastic damping. Extra? Okay. This needs some coffee and donuts. Huh? So if you look at the second page, this is another material, 609. Diad, same material, same general name, I'm sorry. The same general class of material, but it is effective at a different range of temperature. Okay? And the properties are here. The properties are here. Okay? The properties are all what I can find. As function of temperature and as function as frequency. So you take this and then divide it into a grid. Enlarge it so your eyes will not hurt. And then pick points and then put them, generate tables like what I did. And then we want to do master graphs for this material. Once you've done this once, it'll never go away from your head. Okay? The deadline on this, because I was planning to give it to you last lecture. Okay? So we'll extend it to the 1st, March 1st. Okay? Because I was planning this last lecture. So the due date is Thursday, a week from today. Okay? And then the last problem is based on what we covered today and the end of last lecture. Is how to combine them in a finite element to get this. What I want you to do is I did this for a single oscillator. I want you to do for multiple oscillator and see how this response will change. You will see very little change. So don't overkill curve fitting unnecessarily. Okay? You need nice, accurate results, but within reason. Don't make it horrendous. Okay? Now, Yes, now we'll start the second chapter, which is on piezoelectric. Patches. And again, as we described, piezoelectric material can generate electricity if I apply mechanical load on it. So this is stress. And then I'll generate from here electricity. These are electrodes, and then this is the piezoelectric material. Or it can generate strain or deflection. If we apply voltage on it. So this is out. And this is in. And the result will have mechanical deflection. We conventionally used this mechanism as a sensor to bond the piezoelectric material to a structure. When I stretch it to generate electricity, I measure the amount of electricity generated, and this is indicative of the vibration or the strain on the structure. And conventionally, we used this to control structure vibration. The structure is vibrating, give the piezoelectric signal, give the piezoelectric material a signal proportional to the structure vibration, and in the opposite direction, shrink the structure when it's trying to expand, or expand it when it's trying to shrink. So you can bring it to the original position. So conventionally, this was a sensor application. And here, conventionally, it is an actuator. What we will try to do today is to combine these two. Combine these two. I'm not going to use the piezoelectric as a sensor. I'm going to use it as a device to generate electricity. And I'm going to use this electricity to damp the structure vibration. To damp the structure vibration. So once I generate electricity, and you see this in the kids' sneakers, or maybe you have a sneaker that has light also on it. So you have the sneakers, and then when you run, the kids, when they impact the floor, the sneaker generates light. Okay? All these sneakers have piezoelectric material in them. And there's no batteries. You keep moving, you stretch the piezoelectric material, you generate electricity, you put here a little light bulb, and you generate this light spark that you see. So we will not use it as a sensor, but we will use it to generate electricity. This electricity, we use it to damp structural vibration. Okay? So now the purpose of what we're trying to do, use the forward piezoelectric effect, which is this mechanism. This is the forward piezo effect. I'll use the forward piezoelectric effect to generate electricity. And we'll say now here, and then dump this electric power in a source that will dissipate energy. Dump the generated electric power, the electric output, into an energy dissipative circuit. So now what we will have in effect, this whole thing is, I have a structure that vibrates. Then I come and bond on the structure piezoelectric material. Once it vibrates, the piezoelectric material stretches, it generates electricity. So I'll take this electricity and a very simple thing we can do, just take it and dump it in a resistance. This is energy, electric energy generated from mechanical energy, which is the vibration of the structure. I'll take the converted mechanical energy into electric energy and dissipate it into heat in a resistance. So now the result is, any vibration that comes, I'll take it and dissipate it. Very similar to, you have a faucet and then you have a sink. You turn on the faucet, water will come. But you take the water and drain it in the sink. If you plug the sink, the water will keep rising. That's what you have. You have vibration source. Keep exciting. I'm not going to let this source build up vibration. I'm going to take everything that comes from this vibration, push it to the sink. So the structure will stay in a good equilibrium position. Same story for the down here. Of course, I'll get much better performance if I come here also and add an inductance. Come here and add an inductance. This is L and L, resistance and resistance. And this is, for example, a structure that is cantilevered. Now let's take this and make it like this. This is my structure. It has inertia and it has stiffness. So I can write mass matrix and stiffness matrix. I want to damp this vibration. Okay? So I come and put these on it. These two any energy that comes out, I'm dissipating it in a resistance and inductance. There is no sensor, there's no computer, there's no control algorithm, there's nothing. It's completely passive, okay? So this is a shunt of piezoelectric patches, passive. Okay? Now, I take this and dump it here. We know from physics, if I have resistance and inductance, these mechanically are equivalent to a mass and a damper. Mass and a damper. So now we come here. You have mass, and then you have a damper. In a few minutes we'll show that this piezoelectric material has capacitance. And again, from physics, if I have capacitance, this is equivalent to spring or a stiffness. So this little mass, we will show that this is equivalent to L, the inductance. And the damper is my resistance, and the spring is my capacitance of the piezo. Okay? Now we've solved this problem already in vibration 1. We know how this works. If I have a structure, and then on this structure it has excitation, then this structure will look like this. And it will have resonance at some resonant frequency. Now I want to attenuate this vibration. So I come and add mechanically. That's what we did in the first class of vibration. Come and add mass, damper, and a spring. If I do this on a very nice table like this, and I want to damp all its vibration, I'll have many masses and springs hanging. And this would be horrendous design. Okay? Now we have a very nice clean approach. You come, bond this piezoelectric material on it. This piezoelectric material is very thin. And then you can package all these resistances and inductances in a very small place. And then you can damp a very large number of modes of vibration with a very small package. The result is, if I put one piezoelectric patch, one resistance, one inductance to the main structure, the result is I'll split the single degree of freedom system to 2 degrees of freedom. This, if it has very small resistance, R very small. If I increase R, then we should be getting something like this. And the original, this is R, large. The original characteristic of the system this is going to infinity if the structure doesn't have any structure damping. And now I can take this and bring it down. The nice thing here is I bring it down over some frequency band. So this is not like a system that we've done, which is spring mass system. On top of the spring mass system, which was the mechanical absorber, which was effective only at one frequency. Here, when I put this damping, I make it effective over a narrow band. Over a band of frequency, it is not very big, but it is It's a band, okay? So this is over a frequency band. So if the excitation frequency changes from here to here, I have reasonable plateau where the amplitude is small. What we will try to do now is to show the objective that the piezoelectric shunted network, electric network, behaves as a viscoelastic damper. We will show that when we vary the resistance and the inductance, we'll get exactly the same graphs. For example, this is frequency, and then here we can get these characteristics. And I'll plot this as a dimensionless ratio between the excitation frequency and some frequency which is a function of the resistance and the capacitance. And we'll have set of these graphs for different inductance. So now, once you have this, you can generate viscoelastic damping. If you have viscoelastic damping, you can generate viscoelastic damping. Now, if I combine these two, then we have a beautiful design for nice damping treatment. We'll do this next time. Have a good evening and drive carefully. On a plateau. Okay, have a good evening, and we'll see you next Tuesday.